And we start with the team from China, TrueSense, and I would like to give the podium to Chiang, and I hope that I pronounce her name well, her or his name. Sorry. Rick, is TrueSense available or?
If it needs, I'm not planning it is, but we can't find the original picture.
Oh, there.
Yeah, we found it. Yeah. Okay, so we will make him presenter and he can share slides. Okay, take it away.
Hello. Hello, Sensors.
Good afternoon.
Can you hear me?
Yes, we can hear you loud and clear.
Just wait a minute. I'm sorry. I just transferring my PowerPoint to this computer. Is it okay? Okay. Okay. So I'm now sharing my screen. Can you see my screen?
Yes, we can see it.
Okay, thank you.
Maybe it's best to put it on full screen.
Okay. So is it full screen now?
Yes.
Is there any noise of my microphone, or is it great to go?
It's ready to go.
Okay, so who will do the timing, or I just randomly begin?
Just begin, and I think you have a total of 4 minutes, but we're already 3 minutes in the pitch, so please go ahead.
Okay, thank you. So let's start, okay? Hi everyone. On behalf of my team TrueSense, I feel much glad to be here to present to you our 1-year effort on the biosensor for influenza virus. Firstly, let's have a quick look at the overview of our system. The device consists of a cartridge and a detecting box. The cartridge is virtually a full layers organic electrochemical transistor, aka OECT. After adding saliva sample into the vial, we can easily transfer current signal into various concentration by detecting box in an electrical way. Afterwards, the information can be transferred via Bluetooth. We have already finished our app construction and set up a survey, so it is possible to register an online account for your own record. Our OECT is formed with 4 layers. From bottom to the top, it is PET substrate, carbon slurry source and drain electrode, and a UV curing adhesion for insulation, and also a channel which is formed by PSS as a semiconductor. At the same time, we use screen printing for every layer of the OECT that showcase the feasibility for large-scale manufacturing, as well as the lowering of the cost. Our software UI design makes it easier for the users to get the information they want. Concerning the detection of the biosensor, we firstly explored a classical way of using gold electrode with antibody as a probe and 11 MUA for cross-linking. As illustrated, if the amount of HA peptides captured by the antibody changes, the voltage of the gate will change too, resulting in the more or less ion injection into the semiconductor, which will influence the conductivity of the semiconductor too. Then the current between the source and the drain electrode will consequently vary, and the signal will be detected by the circuit of our own design. Then it automatically transfers the current signal into the concentration of the virus by the program. And we also developed another DNA tetrahedron with Aptomer as a probe. This is the 4 stripes and its consequences. As you can see here, it is possible for them to self-assemble. By this means, we can achieve good orientation on the electrode surface and less modifying process, because the location of the sulfur on the 3D structure of the tetrahedron is fixed, and the cross-linking step is not required. To verify the feasibility of such method, we value the voltage potential and electrical impedance spectroscopy. As a result, each step of the modification was proved to be successful. For the whole device, the transfer characteristics curve shows an optimum modulation effect at the fixed gate voltage at 0.4 volt. And the final test shows our devices is most sensitive at the concentration of the virus around 10 to the power of -5, and the limitation can also be lower than 10 to the power of the -9. With electrical magnification, we can achieve even the scale of 10 to the power of -11. So that is pico level, I think. We also developed the model for costume use, and it boasts the combination of sensitivity, user-friendly, minimum invasive because we use the saliva for detection, and flexibility for other using situation. We can only change the probes that we can apply into another domain of bio detection. For conclusion, our system features sensitivity, easy screen printing manufacturing, and innovative in the application of DNA tetrahedron. So that's all for our creativity page. Thank you. Thank you for listening.
Okay, well, thank you very much. And I think it was just a little bit over 4 minutes. That's good. So I think on behalf of the jury, Michael, you prepared a question or questions?
I did. Thanks, Mike. Thank you, team, for presenting your OACT-based sensor. To get us started, I had a question about maybe the fundamental operation and interference. So OACTs, especially PDOT, can be doped with ions, sodium, potassium, which dramatically affect their operation. Can you comment on how you would overcome, in saliva especially, varying ionic concentrations and how it would impact performance, or if you have any plans for overcoming interference that would be in saliva?
Actually, the ions in the solution is the basic conditions that OACT can operate in it, because the ions can go into the channel and the channel can conduct current. So the solution must have ions.
Does the concentration of ions affect the current and your gate voltage?
In the OACT, I think mainly the gate voltage is the main factor that affects the performance of our OACT device. Okay. And I don't think the ion concentration is.
And during our detection process, I think the combination of the HA peptide with the antibody is dominant, and the other ions in the saliva sample, they show that just minus an influence on the gate voltage, and thus it is not too much concern.
Thanks. That was my question for the operation.
Thank you, Jerry.
Okay, thank you, Michael. I had another question. Would your sensor also work on whole blood or serum instead of saliva, or is your platform only working for saliva?
We haven't tested it in serum or whole blood yet, but I think it should work.
And why should it work? Is that of the technology, or so you think that the technology is also going to work with whole blood or saliva or with serum?
Previous articles has proved that the OECT can perform well in the serum or whole blood.
Okay. So any other questions from other jury members? Then I have another one. What is your how is, because I guess that you tested your sensor on artificial saliva. Is that true?
We tested both on artificial saliva and real human saliva, which was collected by our own.
Okay,
Yeah.
okay. What is your experience in respect to the consistency of saliva?
Pardon? I didn't.
Yeah, so saliva sounds like a relatively easy sample, but yeah, I would say that saliva by itself is quite different from, yeah, let's say people to people. So from person to person. How is your experience in that? And would that, and I think that's also a little bit what Michael mentioned. Of course, how would that influence your measurements?
Well, we try to perform a single collection, and then we perform all the tests based on the samples collected on that time, and we do not collect on other person or for another time.
Okay.
So we.
Yes.
Okay, thank you.
We should scale the curves, and when we scale the curves, we're using the same person's saliva samples. So if the curve is fixed, I think it is possible for the detection to be accurate in one situation. Yeah.
Okay, well, thank you very much. I think we're almost close to the time that we have to finish. Are there any other questions also from, let's say, outside of the jury members? Other people? Please raise your hands then. So I don't see any hands. So I would like to thank the TrueSense team, and I propose then we go to the next contestant.
Yeah. Thank you, all the juries. I hope you have a pleasant day.
Thank you very much. Have a great evening.
Goodbye.
Goodbye. Good afternoon. Have a nice afternoon. Okay. We exit.
Next.
All right. If you guys are ready, we can go ahead and get started.
Yeah. So is the team from SensNC already online?
Yep, that's us. We're right here.
Oh, that's you. Okay. Hi. all girls or not?
Oh, almost.
Almost. Oh, there's a guy. There's the guy.
Yeah, we have the girls represented here for sure, which is
Okay, good. Well, if I'm correct, I think it's, and I hope I pronounce the names correctly, Susheta, Shannon, and Sydney. As
that's some of our team
presenters.
members. My name is Grace, and this is
Okay.
Kayla.
Okay, good.
Yep. So, but
Well,
those
I
are
would
some of
like
our
then
team
to propose to, to do your pitch.
Yep. It looks like we don't have sharing privileges right now.
Oh, there you go.
Yeah. All right, great. Okay. Awesome. So let me open this and screen share. You should share your entire screen. Yep. Here we go. It's sharing. Can everybody see this?
Yes, we can.
All right,
All
we will
right.
go ahead and get started then. So hello,
Okay,
everyone.
great.
Thank you so much for coming. We are Team SensNC from North Carolina State University in the US, and this is our creativity pitch. So H1N1 is an influenza type A virus characterized by rapid airborne transmission and high rates of infection. While clinical assays are available, there are no at-home tests for H1N1. So we conducted a survey, and over 90% of our participants preferred an at-home solution for influenza testing to avoid uncomfortable nose swabs, cost of doctor's visits, and the potential of spreading the virus to others. So our team, SensNC, set out to solve this issue by building an easy-to-use diagnostic test for H1N1. We developed an Apta sensor for the detection of hemagglutinin, which is the most abundant capsid protein in H1N1. In our sensor, an electrochemically active aptamer is attached to a gold electrode. When exposed to a saliva sample, the binding of hemagglutinin to this aptamer results in a conformational change, and this alters the electrochemical response. So we measure this via square wave voltammetry, where a change in peak current is directly proportional to that hemagglutinin concentration. So the first step in this process required our team to select an aptamer with a high affinity for hemagglutinin. We chose an aptamer from the literature, which was identified via CellX, with a reported dissociation constant of 15.3 nanomolar. Our team then verified this affinity of the selected aptamer via surface plasmon resonance, or SPR, the details of which can be seen here. We measured a binding constant of 27.9 nanomolar, which is highly comparable to that established in literature, thus confirming the viability of our aptamer for hemagglutinin biorecognition. This binding constant is also significant because it indicates a potential for successful detection at biologically relevant levels, which is about 500 molecules of hemagglutinin per viral particle of H1N1.
Next, we procured the aptamer with a terminal cysteine modification for attachment to gold electrodes, and the free end of the aptamer was modified with methylene blue as an electrochemical reporter. A self-assembled monolayer was formed on a gold electrode, and MCH was used to backfill the aptamer layer to reduce non-specific binding. Next, we designed an electrochemical system for transduction, utilizing a 3-electrode cell plugged into a custom portable potentiostat that runs square wave voltammetry. We integrated a system-on-chip potentiostat, an IR temperature sensor, and a microcontroller, with results presented onto an LCD screen. Benchtop testing was used to create a database of calibration values, which correlates concentration to current peak magnitude. Thus, results can be output as quantitative viral load concentrations or qualitative diagnoses. Preliminary testing of our Apta sensor exhibited a dose response for hemagglutinin. With increased hemagglutinin concentration, our sensor shows a proportional reduction in peak current. Our Apta sensor was tested in artificial saliva and operated over a dynamic range of 0.6 to 9,000 picograms per milliliter, which is the clinically relevant range. We tested our sensor at both 0 and 120 seconds delay and compared the results. Comparable results were realized for both incubation periods, suggesting our sensor response time will be significantly less than 5 minutes. This is the first example of square wave electrochemical detection for a hemagglutinin Apta sensor.
So moving forward, we plan to simulate the sensing of complete influenza virus particles by functionalizing nanoparticles with hemagglutinin. Additionally, we will design a more patient-friendly microfluidic cartridge for saliva collection, similar to the design you can see on the right there. In conclusion, our Apta sensor achieves clinically relevant hemagglutinin detection via an aptamer functionalized electrode and square wave voltammetry transduction. The technological feasibility of our established sensor and the need for accessible point-of-care virus testing suggests that in the future, our technology can be applied to solve a wide range of viral detection needs. Thank you so much for your time.
Well, thank you very much for this pitch. And I think from the jury, I would like to give the word to Philippe. I think Philippe prepared a few questions for you.
Yeah, just one. Thank you. I'm Philippe from EPFL. So really nice technology, good, nice talk also, very clear. I have a technical question. So you immobilize the methylene blue right at the end of the aptamer, if I understand. And so what's the exact role of the methylene blue in terms of this, in terms of the signal? Is the location so important?
Are you asking if the location on the aptamer is important?
Yes.
Yeah, so the reason that we immobilize it on the end is so that when the aptamer itself bends, you could see in that graphic that we had on the screen during the principle, that then the location, basically that conformation change means that there's a difference in the distance between the surface and the methylene blue. And so that is what gives us the differences in the peaks, is how much methylene blue has been towards our surface. So, I mean, I guess if you're asking maybe if it was on the middle, then I guess there still would be a conformation change that could be detectable, but by putting it on the end, you're getting the maximum conformation change because it has like the longest, I guess you could say, radius to bend.
Yeah, sure. Okay, it makes sense. Another question is that in your measurement, it's about the measurement time. So do you measure continuously with the sensor, or do you apply just after 5 minutes, for example?
Yeah, so in the delay that we showed, it was 0 seconds and then 120 seconds. So what we did there is in our testing, we were pipetting on to our electrode. And so we'd pipette, immediately take a measurement, and then just let it incubate for 120 seconds and then take another measurement. So since we were doing voltammetry, that's like an applied peak. So we weren't doing continuous sweeps all the way up, just one at 0 and one at 120.
Okay, and last question, how do you control the aptamer density, and how is it critical to control, in fact?
Yeah, so as I'm sure you know, controlling the aptamer density is very important because more aptamer could be more response. And so in terms of reproducibility, that's really important. So right now, what we're doing to control it is we just have as controlled as possible procedure on our end in terms of making sure that we have the exact same concentrations and the exact same volumes that we're pipetting. And since we're using a commercial electrode, the working electrode itself is blocked off by kind of a ceramic ring around it. So it's very easy to make sure that we're only getting our aptamer solution on to the gold working electrode. And in addition, our MCH blocking step also helps make sure that we have some continuity there. But it also is something that we're looking to improve, and we're looking at maybe doing something that reduces human error by using a machine to apply our aptamer solution when we're functionalizing and things like that. So that's our current solution, is controlling it as much as we can, but we have a few ideas moving forward of how we can improve that as well.
Yeah. Just a side note, if the density is too high, it might decrease your signal also, because the surface is too crowded.
Okay.
And yeah, so be careful with that.
Okay, thank you.
Thank you very much. Very good answer.
Thanks so much.
Thank you very much, Philippe, and thank you very much to the team. I had another question, maybe a little bit related to Philippe's last question. How do you envision mass production of such a sensor? Because hey, you most probably will not need 100, but you need maybe 100 million of them. How is that with your technology?
So for mass production, we're really going to focus on functionalizing the electrodes that we distribute to the individual customers. So the production of the physical biosensor itself won't be really too difficult to maintain. Usually the person will buy one product of that, but then they have to keep recurringly buy functionalized electrodes so they could use the sensor. So the primary focus in the future, whenever we distribute our product, would be the functionalized electrodes that the customer approaches to find out if they have H1N1.
Yeah, and I would also say that our team currently is looking into some different long-term stability measurements. And so we've been looking at what it looks like if an electrode is functionalized one day and tested immediately once the blocking step is over and it's ready to go, or if we keep it in the fridge and how long can we still get that same measurement keeping it in the fridge. We don't have super robust or high sample size for that data yet, so we can't, draw any clear conclusions, but that is something that we're currently collecting data on.
And then I guess that preferably you want to store it not in the fridge, but at let's say room temperature. I guess.
That would be ideal. Yes.
Okay. I have another one, but that's more a clinical question. But why does everybody want to measure the type A influenza and not the type B?
I don't know.
Does
anyone know?
Is H1N1 a type A influenza?
Yeah.
You've never asked yourself this question.
No, we haven't.
No, I know I can give the answer because the type A, I think people get much more sick from type A, and type B is much less in that respect. So that's why you're much more interested in measuring type A than type B.
Thank you for that.
Then also a question that I asked the previous team: would your sensor also work in whole blood or serum?
Yes, it would. Apta sensors in serum have been shown in the literature previously. So we have high hopes for ours that if we were to test it, it would have the same or similar results.
Okay, thank you. Are there any other jury members that have questions? Okay, I prepared another one. So, what is your personal idea about saliva? I think saliva sounds like a relatively easy sample and it's relatively easy to collect. But have you looked into consistency of saliva in respect to, let's say, person-to-person differences?
So
I think we've kind of thought about like that because if someone like maybe was working out or exercising or depending on how someone or when somebody is taking that sample, we're able to dilute the sample so that way we can make it usable depending on how much hemagglutinin we're able to find in the saliva if we need to dilute it or if it's workable just depending on what sample we get, and then just testing like different dilutions of that sample to find out which is going to be most beneficial to test in our sensor.
Okay, well, thank you very much. I think we're almost there in respect to time. I would like to thank the team very much for the pitch and for your answers to our questions. And lots of success with, of course, the rest of this Census event. And wishing you already a good weekend.
You too. Bye-bye.
Thank you.
Okay, bye-bye. Well, I think we already see the team from Denmark is preparing itself.
Hello. Can you hear and see us?
Yes, we can hear you, we can see you, and we can even see your presentation.
Nice. That's great.
So that sounds that we're ready to go. I'm not sure whether we're a little bit now. I think we're good. I think we're 1 minute ahead of schedule, but that's always good to be 1 minute ahead of schedule. So I would say, and I think it's Ashwin and Mats that are doing the presentation. Yeah. Is that correct?
Yes.
Okay, then I would say, well, take it away.
Thanks. Hello, we are detectives from Denmark, and we are here to present to you our biosensor to beat influenza. Influenza is a big problem due to all the hospitalization and deaths that occur every single year, but not only for humans. In 2009, the swine flu made us aware that influenza can migrate into and from livestock production. In Denmark, we have a large pig farming industry, which accounts for 5% of Denmark's exports. This shows us just how important the pigs are for us. Pig farmers struggle to meet new EU regulations and SDGs, such as improving the welfare of pigs and reducing the use of antibiotics. The current solution is the surveillance of pigs, where veterinarians go to the pig farms, collect saliva samples, bring them back to the lab for analysis. However, the pig farmers have to wait 3 to 7 days until they get a result, in which time the disease is likely to worsen. We plan to be first movers and offer a rapid diagnostic tool, which provides an answer whether the pigs have influenza and quantifies the viral load. The farmer is therefore able to know the gravity of the infection and able to implement a more sustainable and responsible livestock production and reduce the misuse of antibiotics. Our sensor consists of 4 steps. Step 1, the sample is collected and tested using a lateral flow assay. Step 2, a color change indicates the presence of influenza. Step 3, the device processes the color change and quantifies it in step 4, where the readout gives a concentration of the viral antigen, all within 5 minutes. Our solution is a lateral flow assay, an inexpensive and easy to manufacture component, which has a straightforward and simple sample handling. The sample is applied into the inlet of the cartridge, where it travels by capillary forces through the LFA membrane. If the influenza antigen is present in the sample, the antigen binds to the detection antibodies labeled with gold nanoparticles in the conjugation pad. This complex then travels to the reaction membrane and binds to the capture antibodies on the test line. The collection of the gold nanoparticles induces a color change. From here on, the device takes over.
Exactly. So we've also made a device, and this device is made with a focus on cheap components in order to enable mass fabrication. This means that it features a microcomputer in the form of a Raspberry Pi, and it's made in a way so that it's simple to assemble. More than that, it's even featuring a portable design in order to be a lab that can be used in the field, being portable anywhere using, for example, solar cells. On board, the microcomputer in the form of the Raspberry Pi will be able to use an algorithm in order to actually use the images from the lateral flow assay and interpret them as a concentration of viral load. This algorithm works in the way that it's basically capturing an entire video of the color changing, and then we extract a region of interest, looking at exactly where the blob or the color change happens. And then by looking at how the color changes, we can do regression models using ridge regressions in order to see exactly what concentration this should amount to using our calibration curves. This means that the user using our cartridge will be able to have a simple workflow with adding a sample to LFA, inserting that into our box, and then getting a readout on an app we've developed directly on their own phones so that they can interpret their results in real time and also have access to debugging. In total, that means that we're moving over to a rapid testing system based on very cheap testing in the form of lateral flow assays, and a field lab in the form of a microcomputer, which means that we'll be able to move from a reactive to a proactive approach in order to do risk-based virus detection. Thank you.
Okay, well, thank you very much for your pitch. And what I do see is that from the jury, Masoud has prepared some questions for you guys.
Yes.
Yes, thank you. This very nice pitch, very clear cut, and I have a couple of questions. Yes. So when it comes to the sensitivity of your assay, so basing on the knowledge that you have from LFA-based sensor in the literature, and also the reagents that you have used, for instance, the KD for the antibodies things. So how do you calculate if you haven't measured empirically the sensitivity of your assay? Do you think that you will reach to this low picogram per ml sensitivity?
It really depends on which type of antibodies we use. Initially, we wanted to use nanobodies, which are more specific, more sensitive. But we tried to find some research groups, and we actually had a plan to work with them. But in the end, they didn't have time enough to develop a nanobody for the influenza hemagglutinin. So we went ahead with the commercially bought antibodies, and to find the sensitivity, we would do a limit of detection experiment with a large number of concentrations, and in the end, we would see how far we could go with our LFA sensor.
So following up questions is also was about the, you mentioned that you can detect the target within 5 minutes. So yes. Do you think that is depending, what is depending on for the reagent that you use? Is it possible, do you think, with the reagents that you plan to use or you have used?
Yes, definitely. Yeah, we can already see the color change, which is in the important part. And even more importantly, currently we're only using rich regression, which means we're looking at historic data from within, I believe, currently 2 minutes, which actually yields results. Mm-hmm. But what we will be able to do actually as we develop, because we did have some ordering difficulties due to some outbreaks, sadly. But that means that we can actually go and use something like time series analysis and such in order to even further minimize the time when we actually have something up and running, which we have sort of the proof of concept with the rich regression, which can then be improved as we're able to do k-fold cross-validation and so on in order to improve further along with our algorithm.
So we expect to go down to 3 minutes.
Okay, sounds good and promising.
Yes.
So you use the gold nanoparticles for detection antibody, wasn't so?
Yes. We functionalize the detection antibody with gold nanoparticles. Yeah. So we get the signal when the secondary antibody binds to the hemagglutinin.
So, and if I remember correctly, it's about 40 nanometer.
Yes, 40 nanometers.
But have you tested different sizes of nanoparticles to see which is most optimal?
Yeah, we tested 20 nanometers and also 80 nanometers, but throughout the different concentration rates from 1 picogram to 10,000 picogram per milliliter, the 40 nanometer had the best signals. So we went ahead with that one.
So now you have, of course, you tested your biosensor with the protein, but if we going the whole way to detecting the particles, so virus particles, what will be the differences? What is the potentially maybe better, or what will be the struggling part?
Initially, the hemagglutinin protein will also be present in abundance in the entire influenza virus particle, so it wouldn't change much our device at all. In terms of struggling,
I think the most important part will be essentially the membrane, looking at whether when we change to actual saliva and you suddenly have something, to make sure that it's not clogged up, and for example also making sure that when we are targeting pigs, that there's not something that would suddenly interfere with that, and that will probably what you would be most important when changing over, because the algorithm in itself will not change, since we're simply looking at when the particles they are captured, and we'll be able to just make new calibration curves without any problems, since we already have the framework and the device designed and up and working.
Do we have time for one more question, Mike?
Yeah, sure. Yeah, sure, Mr.
So for conjugating your antibodies or immobilizing them, what kind of chemistries have you used, and did you test different way, and do you have a feeling or factor for what is working best?
We did initially test with what we do right now is physical absorption of the antibody to the membrane. Initially, we were considering testing a lot of different immobilization techniques such as EDC, NHS linking, and dials and stuff like that. But we ended up choosing the physical absorption because it showed the highest signal. We also improved our immobilization by changing the pH of our buffer, which the antibodies were in, and we actually could improve the signal by that.
But for the gold nanoparticle, how did you immobilize or conjugate it to antibodies?
We used Abcam's manufacturer instructions to functionalize that. It basically, you take the antibody, you dilute it to a specific concentration, you apply it with a reaction buffer that changes the chemistry of the antibody, and then you can functionalize it with the gold nanoparticles when you insert it into the vial with gold nanoparticles.
Okay, thank you very much. Nice.
I have also some other jury members have questions for the team from Denmark.
Can I ask a question, Mike?
Sure. Go ahead, Michael.
Thanks. Really nice talk. I had a question, maybe following up on Masoud's, going to the next stage. You talked a lot about the physical transduction and this potential for either a repository of data or using SOCs to analyze this. LFAs have a lot of problems with environmental conditions for imaging, lighting, things like this. Have you guys thought about how to overcome the quantitative limits or making a quantitative measurement with a camera or imaging system? If this is outside, if this is at a home,
Exactly.
I don't know if you saw the lights keep going off in my office. How do you deal with those things, and how might you deal with those things?
So the way that we're dealing with it right now, and that is actually why we're focused quite a bit on device development, is both making it ready for example, injection molding, but it's actually creating a box where the lighting conditions are completely the same and consistent throughout experiments. So we're using the exact same diodes in the lighting box, and we're powering it by a 5-volt source. So we should be able to have very consistent lighting conditions throughout testing. And of course, something you could also do if it turns out that it can still be problematic is when you're shipping the device, actually also ship, for example, a calibration device so that you can actually calibrate the colors to that exact camera in the environment that it's going to be used.
Gotcha. Thank you.
Okay, well, maybe I have one additional question related to this as well. What is your general view, let's say, on the precision of a lateral flow? Because there, I think for a qualitative result, I think yes, but for quantitative results, what is your view on that?
It really depends. It really depends on which type of antibodies you use, because we've had some issues with batch-to-batch variability between the antibodies that we bought commercially. So if you can sequence these nanobodies that I mentioned earlier, you would have much more precision and much more reliability in the sensor. Of course, LFAs are stigmatized to have not that high precision compared to PCR and such, but they make up for it in their rapid detection and easy user friendliness.
Okay. Maybe one final question. How easy is it to get saliva from pigs?
So basically, we talked to a lot of veterinarians about this. So what you do is you put up these ropes inside the pig stalls, and the pigs will automatically go there and bite on them or chew on them. And this will leave saliva on the ropes, and then we take the ropes back and we can get saliva samples from it.
Okay, great. Well, interesting.
Very.
Well, if there are no further questions, I would like to thank the Detectors team for their pitch and all their answers, and good luck with the remaining event.
Thank you so much. Thank you.
Okay, thank you very much. So I think, Rick, then we have the team from Germany, the iSense.
Yeah, we got message an hour ago that iSense will not be pitching, so we have a break for 15 minutes. Yeah, I haven't. Yeah, you can go to the toilet, take a short break on 15.45. We will be back for the next team for the Influenza, and I saw them already in the meeting, so that's good. And we can start there.
Yeah. Okay. Yeah, I also saw the team members already. Yeah. Okay. Talk to you then in 14 minutes.
Yeah.
Okay. Enjoy your bio break. Okay, I think, Rick, that we can start again.
Yes, we can commence the meeting again.
So the next contestants are coming from Glasgow, Influenza, and I think it's going to be presented by Hasita, Ilse, Jacob, and Jin Feng. So I'm not sure who I can give the word and the podium.
Yes, I will share the presentation.
Okay.
Can we get Jacob as a presenter too, please?
Like Ilse.
Yeah, and
if he raises his hand, I can make him presenter.
okay, Jacob he's raising his hand, I think.
Yeah, he is.
There.
Can you all see my screen?
Yes, we can, Ilse.
Okay,
Jacob, are you okay?
ready?
Can you hear me?
Yes.
Yes.
Fantastic.
Okay, then I'll start. Well, hello everyone, and thank you for coming to the Influenza's creativity pitch. Today, we will present you the Influenza's concept for an efficient and sustainable biosensor for influenza. Every day, 1 million COVID tests are sent to landfill after one single use. Looking at the NHS goal of zero net carbon emissions by 2045 and the prevalence of the climate crisis, it's evident that single-use tests are not viable for the next generation of diagnostic solutions. The Influenza solution makes use of a molecule that captures the H1N1 or hemagglutinin. The presence of the captured molecule results in a difference in impedance that can be measured. Denaturation after heat treatment causes the hemagglutinin to be released, and the cartridge can be washed using 7M urea. Significant advantages of Aptomers include rapid in vitro manufacturability, ease of controlled chemical modification, and the potential of long-term storage and transport at room temperature using lyophilization. To limit the nucleus degradation, artificial L-DNA was used to create the Aptomers, and the heat treatment will denature any nucleases on the cartridge within 5 minutes of testing, minimizing exposure time. From this, we estimate that our Aptomers will withstand at least 8 tests before any notable loss of performance occurs. 8 cartridge uses means 8 times less waste. The V46 Aptomer, selected for its high affinity towards both the HA stem as well as the whole H1N1 virus, forms the molecular recognition element of our biosensor. A chain of functional groups initiated by aminopropyl silane covalently bonds the Aptomer to our substrate, as shown in the diagram. This carefully constructed chemistry of the cartridge ensures that the Aptomer has a greater binding rate and can withstand the recycling process. Now Jacob will take you through a step-by-step animation of the cartridge.
Okay, this animation shows our testing and recycling process. Firstly, the sample is added, and it's left to incubate for 2 minutes. Next, a PBS wash removes the remaining sample from the electrode, after which the impedance reading is then taken. For recycling, a hot water bath at 95 degrees is sufficient to denature the Aptomers, causing HA to be released from their complexes. The 7M urea wash then removes the unbound HA from the electrode. Finally, it is left for 15 minutes for the Aptomers to reform before the test cartridge can be reused. Our IDE contains 400 Aptomer binding channels as shown in this diagram here. Our EAS assay measures the difference in impedance across each channel caused by the presence of that captured HA against the reference impedance, or PBS. ID is modeled as a serial connection of a double-layer capacitance, solution resistance, and impedance of the Aptomer HA complex as shown, where each Aptomer HA complex is equivalent to an RC cell. The model bow plots of the Aptomers before and after binding to hemagglutinin show a clear difference in impedance. This is most significant at 40 kHz operation. The slide here shows the structure of our cartridge, including microfluidics channels, PBS reservoirs, and the IDE. We use a unique push-button mechanism to release PBS at each test, which simultaneously records the number of times each cartridge has been used. Each test is conducted via a reader unit into which a cartridge is inserted, and the test result is transmitted via Bluetooth to our mobile app, which contains a record of results, testing instructions, and guidance for ease of use. Despite a challenging experience in SensUs this year due to a lack of lab access, we believe our unique biosensor sets a precedent for a new, sustainable future in healthcare. Thank you very much for listening.
Okay, well, thank you very much, Ilse and Jacob, for your pitch. So from the jury members, I think Vivek prepared some questions for the team.
Yeah, thank you, Mike, and also thank you to the Influenza also team for the nice presentation. First of my questions also is about the physical transduction mechanism that you propose with the sensor platform. So it was argued that the conformational changes so is what you are detecting. So is this an assumption right now, or how sure are you about that?
Yeah, so let me just clarify that. So since we were doing our experiment, our project online, since we weren't able to do any actual practical experiments, we've identified two criterias for what we can detect as impedance change, because we can detect the presence of the HA between the electrodes, as well as the impedance change that's caused by the conformational change of the aptamer. So there are two separate components of impedance that we can target. Unfortunately, like, we're able to evaluate and model the presence of the HA impedance value better using our modeling software without doing any practical experimentation. So we focused on that section for our report, whereas we understand there is a conformational component as well arising, but we would need to test this practically to identify what's the actual conformational change, impedance change that happens due to our particular aptamer binding with HA.
I don't know if I'm getting this wrong, so maybe you can have a look later on. Normally you want to retain the conformation of the aptamer, so that is why you would have a specificity toward the biomarker you want to detect. So this is important for the ligand binding. This is not clear to me, so but we can move to the other question. The fluidic cartridge that you designed, so I think it looks so quite nice that you have a provision for many samples. But the sample is then going to the same sensor. So do you have a differential design? So for the sensors, this is not clear to me. So how would you multiplex out of this sensor platform?
Do you mean how we would adjust the biosensor for other virus strains?
Yeah, so you have provision for 8 samples, as I understand.
No. So can we get the presentation up, Ilse, again, just to clarify that? With the cartridge outline?
This one or?
No, the one with the labeled cartridge, that one, yes. So in this one, Vivek, so we don't have 8 samples that are going into the cartridge at once. Our only sample input chamber is the one at the top that is labeled as the sample input chamber. The other 8 chambers are hosting reservoirs. As you can see, there's a small pouch as labeled in the cross-section view at the bottom. So they house these pouches for the PBS, and they're meant to be used one at a time for each test, since our cartridge is designed to be reused 8 times. So our sample is only added in the input chamber. So one test cycle, as Jacob demonstrated in that animation, is one full cycle. After that, the regeneration process happens. Then we use the second buffer with a second sample.
Mm-hmm. Yeah, so this may be also one of the advantages using aptamers, that your sample platform is maybe also good for the regeneration. But have you so far benchmarked the regeneration process? Maybe not electrically, but maybe with the supporting technology.
What do you mean by benchmark? Do you mean like how we designed it, or
the regeneration process?
Yes, the regeneration process. What aspect of it is your question about? What aspect of the regeneration process?
So you want to use your sensor platform for many samples, one after another.
Yes.
And you need to regenerate your biofunctional layer, which is the aptamer layer. Is that correct?
Yes.
So have you evaluated this regeneration?
Yes. So based on literature, people have tried to regenerate aptamer layers before. And similar experiments have also been tried with saliva samples as well. And using our aptamers, which are made with LDNA for enhanced nuclease resistance, we found papers that suggest that aptamers are able to survive in saliva samples for up to 45 minutes. So that's why we've limited our test to under 5 minutes. So that way we can use our cartridge up to 8 times. So 5 times 8. And the regeneration process is very simple. So we apply heat treatment at 95 degrees for 10 minutes, which basically denatures the aptamers, releasing the previous sample's HA back into the solution. Then we wash with urea solution to remove that unbound HA from the previous sample. And then we reform the aptamer by leaving it at room temperature for 15 minutes. So that's our recycling process. And aspects of this has been tried by other people in research, but we've put it all together. We've identified the use of urea as a suitable washing buffer for the recycling step because it's non-toxic and its properties allow us to not harm the aptamer binding to the electrode layer. So it doesn't affect that aminopropylsilane binding that we're using. And we've also set it up in a way that it's also beneficial from the business aspect for translation, which allows it to be used in commercially without outside of a lab.
Yeah, so one last question I have. How do you think your sensor platform can be adapted to detection of different subtypes?
Yeah, I think we received a similar question on Sensors Connect as well. So in terms of multiplexing, our idea is we have two potential ideas. One being segmenting our IDE into sections with one aptamer in each section. So our sample will flow through the entire electrode. So it will be exposed to each aptamer region in the IDE. So that means we're simultaneously able to detect different viruses using different impedance signals, obviously. So we need essentially multiple connections to our reader unit, but it's preserved within that one system. So we're able to detect, say, 3 virus strains at once using one cartridge. That's our proposed system. We haven't experimented with this, so obviously there'll be practical considerations to take into account, such as because as the sample flows through, we lose some concentration as the HA will bind to the first aptamer first, then the second aptamer, then the third aptamer. So there'll be a gradual profile. So these are practical considerations that we've understood, and we will test as soon as we are able to do in the lab. But so far, we haven't been able to gain any lab access for the competition.
Yeah, okay. Thank you.
Okay, well, thank you, Vivek, for your questions, and of course to the team for the answers. If I understood correctly, I think you're going back also to your regeneration. Are you then treating the entire, let's say what we see here on the screen with the ureum and the 95 degrees Celsius heat treatment, or is it only the sensor surface?
So we are able to dip the entire cartridge in 95 degrees boiling water because all of the materials and the binding elements we've ensured are able to withstand 95 degrees temperature, and we're using a water bath, so there's no additional chemicals being added. The urea wash will be inserted into the sample chamber, so that will just run through the entire flow system and wash out unbound HA.
Just to add to that, maybe you're a bit confused with the reader unit, which you can see here. That's the only thing that will not be dipped, will not be regenerated because it won't be needed.
Yeah. And
That's
another question to Ilse is, in your presentation, you mentioned that you are going, or that the intention is to lyophilize. How do you see lyophilization in mass production of your cartridge?
Sorry.
Yeah, so lyophilization, let's say, in respect to mass production, is quite it's quite a challenge, I would say. Have you considered just drying instead of lyophilization?
So can I answer that one? Yeah, can I answer that one because I was more involved.
Very shortly, please. Short, please.
Yeah. So the reason we chose lyophilization is one option, which is particularly used with aptamers, and the reason why we propose doing it is since our cartridges are so small. We believe it is a rather expensive technology, but doing it in mass scale by packing all of the cartridges in a smaller space, we're able to store a lot of cartridges at once. And so basically the density of tests that we can store for a long time under lyophilization is very high. So it's very useful for like remote applications or where you're not able to transport the cartridges very easy to such locations.
Okay. Well, thank you very much, team, in respect to your pitch and the answers to the questions that the jury members had. So good luck with the rest of the event, and wish you a lot of success.
Thank you
very much.
Thank you very much.
Bye.
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 Okay, then we will move to Egypt. I think AUSense is next on the list. And as a presenter, I have here Salma. There is Salma. You're still on mute or not? Not anymore.
Can you hear me now?
Yes, we can hear you loud and clear. Thank you.
Okay. 1 minute, I will share the presentation right now.
Okay.
Can you see the screen?
Yeah, can you maybe put it on full screen?
Yes, I'll do that.
Okay, good. Well, the floor is yours.
Okay, thank you. So greetings, here is Team AUSense and for the presentation of creativity. So first I will start talking about the aim or the purpose of our biosensor and then the idea behind it, our methodology and the simulation and modeling that we did, and finally the limitations and future work that we recommend. So as we know, many viruses have endangered the world in the past few decades, and actually influenza A virus is no exception. So many trials have been taking place for easy and early diagnosis that will thwart the infection outbreaks, because according to the World Health Organization, about 1/3 of the world population have been infected by the virus. And scientists now are trying to approach biosensors since they are sensitive, cost efficient, and most of all, they allow personal use, unlike previous methods such as the virus isolation, which is time consuming, and the PCR, which is not easily accessible. But to develop a biosensor, we need a major compartment of the virus that we have to target, and we couldn't have something better than the hemagglutinin protein, because it's, first of all, they are located at the surface of the virus, and also they play a major role in neutralizing antibodies. So we had to develop a biosensor that targeting hemagglutinin 1 protein in influenza A virus. So our idea depends mainly on using magnetic beads, streptavidin magnetic beads that binds to bionylated polyclonal antibodies, and all that structure with the polyclonal antibodies specific to the hemagglutinin protein will bind to hemagglutinin antigen present in the sample, and all that antigen antibody complex will be loaded onto a gold imprinted electrode that have RNA aptomers on it, and those RNA aptomers will play the role of attaching to the antigen antibody complex, and at the same time will be immobilized and reduced to give us potential difference that will be read by the potentiostat, and finally will be translated into concentration readings. But to do so, we had to pre-process our samples and treat them first with L-cysteine ethyl ester and BBS buffer, because mainly they will decrease viscosity by disrupting the disulfide bonds in the myosin found in saliva. And then we will mix that reagents with the samples that possibly containing hemagglutinin. Then we will use magnetic separators to immunoprecipitate the solution, and then we will take the precipitate and load it onto the gold imprinted electrode. And that electrode we will treat it first by immobilization through DTT reduction, and after that we will treat it by 6-mercaptan hexanol, which first will allow the immobilization, and second it will block any remaining gold particles on the surface. After that, the potential difference or the signal would be transduced through the palm sense for potentiostat, and then it will be translated through mobile applications that have pre-implanted concentration or calibration curve. Also, we have supported our biosensors through simulation using several modeling. So we had performed 2D modeling through Vienna software, 3D modeling through RNA Composer, and finally the docking by Hex software. And as we can see here in figure 4, the balls and sticks represent the aptamer that will bind to the hemagglutinin protein represented by the wire form, and that gives us a total score of -316.62, which indicates a successful binding. So our biosensor indicates here a successful binding through the Aptomer and antigen, but we have limitations that we faced, and we would like to work on it in the future. So the limitations were in terms of the increased time and the use of multiple reagents. And since we have used antibodies for the enrichment kit, that possibly we infer that will delay stable readings that reflect concentrations. And we recommend for or suggest for the future application to decrease time used during testing is to add on microfluidic cartridge that will act as an alternative to the enrichment kit. And actually, those will automate the process for us, and at the same time will decrease human interference during testing. We have also sort of redesigned our recognition molecule to be an aptamer attached to a branched DNA or amplifier, because that will boost or makes a faster redox reaction. On the other hand, regarding the multiple reagents problem, we have thought of using pre-filled syringe, and that would be an alternative to the enrichment kit because it allows mixing fixed amount of the sample and loading them directly on the imprinted electrode. Finally, we could have used a smaller device like the MSTAT Pico development kit that will be directly connected to the mobile application. So eventually, our biosensor helps in the diagnosis of influenza A virus in a sensitive and cost-efficient way, and we have supported the successful binding through modeling and simulation. However, we have faced some limitation, and those we will take them into consideration for future work. By this, we reach the end of our presentation, and here are our references. And thank you for listening.
Okay, well, thank you very much, Salma, for your pitch of your technology, your sensor. And from the jury, Michael prepared some questions for your team.
Yeah. Thanks, Mike. Thanks, Salma, for the nice presentation. I had first a technical question on your transduction mechanism. So I understand the molecular recognition is the magnetic beads capture the hemoglobin, and then it's almost like a sandwich with the aptamer segment. How exactly is the electrochemical transduction done? What's the principle for detection and the mechanism of operation?
Okay.
And sorry if I missed it. It wasn't clear to me.
Okay. Thank
Okay.
you for the question. My colleague
Thank you,
Yahya
Salma.
would like to answer that. You're welcome.
Yes. Can you hear me?
Yes.
Yes.
Okay. Sorry, the question was, can you please repeat the question because I was trying to.
Sure. So I understand the molecular capture and recognition portion, but I was unclear of the physical transduction. So what was the electrochemical principle or method that's being used to quantify the
okay. Okay, actually, there was reported in the literature that the reaction between the aptamer and the antigen itself may generate like a redox reaction. So this will be I think the potential. This is the thing, and we are trying to also see the impedance using the potential stat. The presence of magnetic nanoparticle and this and attachment on the surface will lead to will lead to a difference, a potential difference, and impedance difference that can be detected using the potential state.
Okay, so potentially.
Yes, this is the main thing, the impedance. Yes, the impedance, not a redox reaction, because it won't happen. Sorry. Yes.
Sounds good.
So the main thing is the impedance.
Okay, thank you. The second, or a follow-up to that was, since you're using magnetic particles, and in the ultimate sense, we would like to detect viral particles, do you see any issues with maybe the size of the magnetic particles versus the size of the viral particles and getting an accurate quantification of the total sample or concentration of, let's say, viral load in the sample?
Sorry, it was freezing. The connection was a bit. I think what I got was the magnetic nanoparticle
and so the viral particle. Do you see any issues in going from protein, so hemagglutinin in solution, to detecting a viral particle, like the whole particle?
Okay, I think it will be easier to detect a viral particle than detecting an antigen, since a viral particle will use more than one magnetic nanoparticle because it will has more than an antigen, so it will decrease, it will amplify the result. However, we will have a problem with the linearity or the reproducibility of the results in different concentrations if using a viral particles. So we will need to optimize our biosensor to be more linear, or to detect certain or control the number of magnetic particles interacting with the viral particle. Okay.
Yeah, thank you, Mike. Those are my questions.
Okay, maybe another question that I have is, what is the size of the magnetic particles that you are using?
It's 0.5 micrometer.
Okay, so 500 nanometers.
Yes, 500 nanometers. Yes.
Yeah. Okay, that's. Does anybody else from the jury have a question here for the AU-Sense team?
Yeah, I just wonder if you titrated the amount of the antibodies on the beads. So did you test different concentration of the antibodies attached to the beads?
Okay, we were planning to do this in our methodology, but actually we did not receive all our reagents, so we couldn't have a working biosensor till the competition. However, we were planning to do this first of all to make like an experiment to find the amount of viral antigen that has attached to the antibodies of the magnetic with the magnetic beads. So we can like see how the yield that comes from using this extraction method.
Maybe an additional question related to your sensor, your technology. Would since now the target is saliva, would this also work in whole blood or serum plasma?
I think it may. Yes, it will work in serum plasma. Since the technique using an antibody or a magnetic antibody was used in other things other than influenza, for example, like COVID. So this technique was used before in COVID. So I think it may work in whole blood, but maybe we can use, instead of iron magnetic nanoparticles, we may use a silica and silica-coated nanoparticles to decrease the interaction with metals in the blood.
Yeah. Okay. Thank you.
And also to increase the impedance.
Yeah. And in respect to let's say, hey, you're using actually the magnetic particle to fish, let's say, for your analyte or not. That's so. What are your thoughts about, let's say, the consistency of saliva in respect to, saliva can be quite different, and let's say in respect to the efficiency of your fishing?
I'm sorry, it's freezing a bit.
No, what I meant is, let's say, due to the fact that saliva is quite different from person to person and can be quite viscously different. The efficiency of your using of your magnetic particles could be different. What is your thoughts about that?
That's why we suggested using L-cysteine to. I'm sorry. So that's why we have suggested using L-cysteine, so that it can break the sulfide bonds in the saliva, and it may decrease the viscosity of the saliva.
Yeah.
To reach the optimum extraction of the antigen.
Okay, well, Jahia and Salma, thank you very much for the pitch and for your answers to our questions. So good luck with the rest of the event, and I wish you all the best and already a good weekend in advance.
Thank you.
Okay, thank you. Bye.
Okay.
Bye.
Okay, then last but for sure not least, we have Upsense, and I already saw that Javier, I guess it is, that he got a very good massage already. So on the screen, so he must be very well prepared, I must say. So Javier, yeah, please go ahead. The floor is yours.
Well, first of all, I would like to ask if you hear me well. Do you?
Yes, we hear you loud and clear.
The massage was excellent. Excellent. Thank you so much. I'm going to share my screen and put the presentation, and I want to check if I can pass the slides properly, and then I begin. 1 second. Let's see. Yeah, it's working. Okay.
Yes, and it's visible to us as well.
Thank you so much. Okay, well, let's do it. Okay, welcome everyone. My name is Javier, and I am here presenting the creativity pitch of Upsense, the team representing Uppsala University from Sweden. We are an interdisciplinary team of 15 students from 13 different nationalities. We developed an automatized technology mostly fabricated via 3D printing for the detection of the protein H1 of the influenza A virus in saliva through an electrochemical chip that uses antibody-antigen interaction. Now I'm going to explain the manufacturing process developed by Upsense. The detection is based on a single-use 3-electrode chips sponsored by Zimmer and Peacock, and we use cyclic voltammetry to characterize the surface of the working electrode. Here is the bare electrode. Now we do gold nanoparticle electrode position, followed by linker plus antibody, and finally we put a blocking BSA layer to guarantee that the protein H1 only binds the surface of the antibodies and not the rest, forming the here complex that we can see on the surface of the working electrode. Our automated biosensor, Influenza 1.0, uses a Raspberry Pi computer that controls the flow to the surface of the working electrode, mediated by 2 valves and a single pump. Thus, the potentiostat makes possible the transduction of the content of the protein H1 in the sample and plots on the screen or on our app the results. The automated detection guided by the Raspberry Pi computer is composed of 3 simple steps. Firstly, we have a 25-minute incubation of the surface of the sample on the surface of the working electrode. We wash it away with PBS, no use of detergent. And finally, we pump our redox mediator, in this case, ferrocyanide, which performs redox reactions on the surface of the working electrode, enabling electron transfer of the ferrocyanide, generating a current. Therefore, the system uses differential pulse voltammetry for the transduction, an electrochemical technique that applies a series of potential pulses in a linear ramp while recording the current. Thereafter, the difference in the current before and after the application of each pulse builds the plotted diagram that is directly related to the concentration of the sample. For an increase of the H1 protein, we will see a quench of the peak current. Therefore, the application of differential pulse voltammetry minimizes the background current and increases the sensitivity, making DPV a suitable technique for the detection of H1. Now, we are proud of our prototype, but in order to truly aid the healthcare system, more work needs to be done. We see the SensUs competition as just the first step in our journey to the safer future. We are Upsense, and we would like to thank our sponsors for making this project possible. And of course, I thank you for your time and your attention.
Well, thank you very much, Javier, for your very nice pitch. So from the jury, Vivek has prepared some questions for you. So Vivek, take the floor.
Thank you. So thank you, Javier, for the nice presentation and the readout, and then all the system integration also looks very impressive. Also, I congratulate your team for that. Coming to the questions, so you took established sensor platform, so these screen printed electrodes, and you decided to modify them with gold nanoparticles. So why gold nanoparticles? Why not something else?
Well, if I can tell you, one of the problems that we saw is that the surface itself is small. So the gold nanoparticles are capable to increase the surface area for detection. That's why we were thinking about, okay, let's increase the surface area. And we were breaking our head, like, should we use mesoporous surfaces? Should we, and we were like, okay, why not going with metal nanoparticles? And we tried silver and gold gave the best results. So we went for gold.
So what do you mean by best results?
Gold, the best electrode deposition, basically. Like the gold was bonding the best to the carbon working electrode. So we decided to stick to that one.
Okay, all right. So you are also using monoclonal antibodies here as a receptor molecule. So why going for these antibodies against the other options that you have? So like Aptomers, which are more stable and which can give you much longer shelf life, if so to say.
Well, the shelf life itself also depends on how you store the chip, right? We also tried polyclonal antibodies, but we saw that the monoclonal antibodies were, the problem is that when you passivate the surface, you don't want very big molecules in charge of doing, you don't want very big biorecognition elements. So we are in Sweden, and we are targeting the healthcare system of Sweden. And here, every country, every pharmacy is going to have, a fridge. So the shelf life of antibodies at the ideal temperatures is pretty long. So we're not really, we have 1 year. Of course, there is a lot of optimization and we want to try more things, but the time span for this project is not as we would love.
Yeah. So I can certainly understand that. Yeah, so the time has been difficult, also for many teams. So regarding the use of the receptor that you're using here, so which should be highly specific. So have you also thought about detecting different subtypes? And do you think it is feasible?
Of different subtypes of antibodies, you mean?
Different subtypes of the influenza.
Of influenza, yes. Well, that's out of the influenza breakthroughs, 50% of them have been with H1N1. And some others that have been small breakthroughs have been always with H1. For multiplexing detection, we will need to consider other options, like, for example, inverted sandwich ELISA or something like that, with another biorecognition element that is very sensitive to another protein or so on. But yeah, of course, we have considered it, and the nice thing of electrochemistry is that you can do multiplexing with another biorecognition element attached to something else, and then just try to follow the spread of the virus or a new strain, as you say. Yeah, we have considered it.
Yeah. Okay. Yeah. So one last question and a general one. So looking back, so through the project timeline. So since you guys started and you put a lot of work into the project, what is the biggest challenge? So for the next stage.
Do you mean next stage or so far until now?
So you did quite elaborate characterizations of your sensor platform. So you also achieved quite good performance for your sensor. What I see from the team report documents, during all this time, all these past months, so that you have spent, so building that platform. So what has been the biggest challenge here?
The biggest challenge from my point of view, I have to say that I could consider myself as one of the main persons in the team, and what I have seen in my team is that when you have really capable people, everyone is very enthusiastic to have its own opinions. So, when you have really smart people, what matters is that you can put them together to work together. So for me, with this team, my only problem is the fact that we are all very capable, So to put all of them together to work, but from a scientific point of view, the facilities at Uppsala University are wonderful and the team members are also wonderful. So I will say the main difficulty is that we are very stubborn. But nothing else.
So you had only good problems to work on.
But problems that are good to have, I would say, because within the team, decided to one or another approach, and I am pretty sure that small competition that we had itself, we had, SensUs, and then we had AppSense itself, and I think that's why we have such a nice, for example, as you say, analysis of the surface of the working electrode, because we were like, so why are we using that? You know, like, so yeah, actually, that's why we were capable to go through. It was a lot of push each other, but in the end, it's a big family, and that is really beautiful to see, actually.
Okay, very good. Thank you.
Thank you.
Okay, thank you. Are there other jury members that have questions to Javier? I have one. Well, Javier, what does the team envision as the end user of your sensor?
Well,
and is that the lab? Is that the home testing? Is that?
No, we are, I mean, as you can see in our report, we are targeting pharmacies, first of all, because pharmacies in Sweden have really good opening hours, and that's really useful. And the people that work at pharmacies are, you know, educated enough to know how to handle the little handling that you need to do with our material, with our chip, which is just put the sample because it's completely automatic. But in order to be able to read something, they need to know a little bit about this kind of recognitions. So we are going to begin by pharmacies, but we are thinking about spreading in the second year to the healthcare system itself. So we are considering, we are not targeting home, like how do you call it, telemedicine, because through our validation process of the business model, we had the chance to talk to really nice experts from the healthcare system of other countries in the European Union. And they told us about the importance of having a biosensor that is useful, but also about the humane part of medicine. So doing home testing is useful, but at the same time, if you don't have the support of someone like a nurse or a doctor there, someone can enter in a crisis. And that's also something to take into account. So we are not targeting home testing yet, but yeah, that's very far in time still.
Yeah, but because looking to your sensor, so let's say to your let's say the instrument, I think it's also rather still rather complicated with flow and everything. So how I think also there, if you want to do home testing, or even already at the pharmacy, I would say that it's quite complex.
I mean, we have a bit of a dinosaur, it's true, but it is also true that, you know, electrochemical probes for detection have been optimized for example, you know, glucose and so on. So if we want to be just sensitive, you know, prove the presence, I think we could do a home testing device. But if we want to have a viral load, I can't tell you yet, but it's something that we want to improve here.
Okay, good. Well, if there are no further questions, I would like to thank the Upsense team for the pitch and the answers to our questions, and good luck with the rest of the event. And I already would like to wish everybody a good weekend.
Thank you so much. Same for you.
Okay, take care. Bye.
Bye.